Okay, I think we'll get started. Well, welcome to the third of our 4-lab sequence in Machine Learning for General Chemistry, Part 1. And we're going to focus, this lab and the next lab will use image recognition techniques. So the last lab we talked about regression techniques that are looking to identify relationships, functional relationship, mathematical relationships between properties. Here we're going to be looking at images, and the setting we're going to do here is in a quality control setting. This is again still in the branch of machine learning called supervised learning. So we will be feeding the learning algorithm an image, a picture, and then we will have what is called metadata associated with that picture. So it's very much like how the images of cats and dogs or whatever are trained. So you give the machine learning 50,000 pictures of cats, identifying those as cats, and then same with dogs, and then it can tell the difference between it learns the difference between a cat and dog via this supervised learning. So is it right, is it wrong? This is the image recognition here is going to be done via what are called convolutional neural networks. I'll speak a little bit about that, although we don't want to get led too far afield, but we want to have some understanding of how it's working. And then again, like I said, it'll be an application to a quality control chemistry. Okay, so this is a new algorithm for us now, convolutional neural network. Convolution really just means taking one function, and in this case, this is going to be a two-dimensional mask function that goes over the image and convolving it or running it past that image. And then it's at any given step there, it adds up the signal. And if it's a stronger signal, then there's a better match of the mask, or the filter, as it's called, mask filter, with that region, that part of the image. So for example, you might have a mask that's just a horizontal slit. Okay? And let's say you have a picture of a square. If we convolve, say it's a horizontal slit, so if we were to convolve like this and like this, when it goes through the top and the bottom of that square, we would get a large signal, but it wouldn't if it was here. Also wouldn't if it's being convolved, say, all the way along this way. So we're seeing that it's picking out the feature of this horizontal line. And we have then a bunch of these filters, and the filters are in different directions. So it picks out a bunch of different features. So how does it work then? There's this input layer that gets the image data. Then in these so-called hidden layers, we have this convolution with these different filter features. And the number of layers here is called the depth of the network. So this is where the deep learning comes from. So we will play around with different depths, a different number of hidden layers. And then there's an output layer that has that end up giving the output, and these get adjusted according to the image data, and each of these nodes are then assigned weights for that. And what this settles into then is the ability to identify different types of images. The larger number of images you have, the better and more precise the data will be. Also, the quality of the images. Okay, so the application we're going to look at here is Polymer, a polymer bead company. So they're making these polymer beads, and they're trying to produce those. And let's just say that when they run a batch, it's very precarious, and it'll either make large polymer beads or small polymer beads, or a mixture. And let's say the company can use a batch that's large, can use a batch that's small, but if there's a mixture, then it's not useful and the batch gets rejected. And to make it even a little more sophisticated, we'll look at a pure large batch, a pure small batch, an acceptable large batch, so there's almost all large, with maybe a few small polymer beads, and vice versa. And then if there's a real mixture, then it will be a rejection batch. Okay, so that's the setup, and so let's go to the computer now and see how this will work. All right, so we'll open this up. Let me get this straightened out. So it's a little straighter there for you. Okay. All right, so let's open up our Chem AI Tree Lab Sequencer Part 1. And if you're just coming to this video from somewhere else, we went through how to set this up on your machine and how to get the data sets onto your machine in the first lecture of this playlist. So I'll direct you back to that. There's a link in the description, so that will help you download this onto your computer. It will take you to the course webpage, and on there will be lots of instructions on and the type of files that you're going to need to download them. But I'll let the previous video do the work on that. So we've got this set up. Let's go ahead and launch now the Polymer electron micrograph sorter. And while that's, I should note, you will get the, we have to have the Windows terminal up, or at least I couldn't figure out how to make this a standalone Windows program without having this up. And okay, this has come up here now, ready to go. So let's look at our lab and then we'll work through the lab together. So we're going to use this pre-trained convolutional neural network, or CNN, and that's what I talked about earlier. The more layers, the more delicate the prediction can be, but also, I should say, you can get into a situation where you overfit. So the question of why don't we just use thousands of layers? Well, that will result in an overfitting case where things that aren't physically meaningful, so the actual noise pattern, gets learned by the algorithm, and then that brings it with it and disrupts its ability to make predictions on new data. So for example, cats versus dogs, if it was overtrained or overfitted, it's looking at the cat, but it's also picking up all the different environments that the cats might be in, and it's so well trained on that that they become sort of part of the cat, and that's not what you want, and so it makes the prediction worse. Okay, so we're gonna look at that, and so we're going to see now how we're going to do this. So let's look at these electron micrographs of polymer beads. This is a real one. It's a picture that is on the Thermo Fisher website for polymer micrograph electron microscopy. So this is what they look like. Here is what I wrote to just simulate that. So this creates an image, and I made various batch sizes, or I shouldn't use the word batch because we're going to use batch here, but various data set sizes, 2,000 images, 8,000 images, 16,000 images, 32,000 images, and 64,000 images. And we're going to train on all of those. Typical batches then we're looking for are pure small, pure big, so we see no big ones here, no small ones. We do see some variability in size, so I added some randomness to the size of the bead. And then here is a acceptable small. It's all small, but just this one large in here. And then this is an acceptable large, although it's starting to be quite a few smalls, but an acceptable large, and then here's a mixture that would be a rejection. Okay, so let's go ahead and talk about the error types that we're going to get here now. So it's been trained. Once it's trained, it will feed it a new image, a brand new image it's never seen, and then it's going to try to make a prediction. And we're going to call a bad error is if it tells us to reject a batch that the company could sell. So let's say it's a pure small, but it says reject it, or accepts a batch that the company should reject. So it's a pure or acceptable, and then it it's a reject, but it labels it as a pure or an acceptable, and so then the company sells that batch, and it's not right for the customer, and so that reflects badly on the company. So that's what we're looking for there. Acceptable errors would be if it says it's small, but it's actually acceptable small. So, or large, acceptable large. And then what we're going to do is identify, we're going to run 2,000 of these images, or, sorry, 200 of these images and get a % error. And I'll probably just run it once. You're going to run it 3 times, take an average to get a sense for what these different levels of training will do. Okay, so let's go ahead and launch this. Hopefully this is a little bit different, the one you're looking at. I'll try to get this updated. So we have the launcher now, and so you don't need to go and find the individual programs. So that's obsolete here. But we will now start to load the training model. So we're going to start with the 8,000 model. So we're going to choose here, and I need to go to the data sets. So data sets, and then PEMsorter. So this should be on your machine now. And then let's go to this. This .caris is the learned model. Notice it's quite big. And this is the trained model. So we're not going to have you trained because it takes a while. The 64,000 one, for example, took my computer running full blast for 14.5 hours. So it, obviously doesn't fit in a lab period. So let's open this. It's already pre-trained. So we'll open this. Now it will load this, which takes a little while. Then it will ask for what's called a pickle file. I'm not sure why it's called a pickle file, but a PKL file and pickle style file. And so we'll just open that. And then it says model loaded successfully. And so we'll hit OK. Now, what we're going to do is press and inspect batch. So here a batch comes to us. We run it, and look at this. This is pure large, right? And then what does it say? It's actual is a pure large, as we can see with our eyes. And then the predicted, it's never seen this particular image before. It's predicted a large, so a pure large. So it was dead on. So and that's going to be in green. If we get an acceptable error, it will be in blue. If we get a bad error, it'll be in red. So let's run a few of these. Oops. Okay. Another large, pure large. Here's pure small, said pure small, so it's doing pretty well so far. Pure large. Here's reject, it says reject, right? So doing quite well. Let me try a few more. It's really doing well. Okay, well, we're well trained. So let's go ahead and run the sort. This will run. Again, if you're just coming here and you didn't do the installation, there could be an issue here. If you hit this and the program just crashes, that's likely because it is trying to write some directories and then files. So it's going to sort each of these images, and if it doesn't have permission to write those, then the program will crash. So you can go back to the first video, and see what the troubleshooting workaround is for that. So I'm going to run this 200 runs. We'll watch these come in. So you'll watch the screen go, and we'll see how this is doing. Okay, I'm going to pause the video and restart this. Okay, I didn't follow my own troubleshooting advice, so I didn't have the folders correctly in the place where this is trying to write to, and so the permissions issue caused it to crash. So just like you might have experienced, then I just went and added those according to the installation troubleshooting guide, and it seems to be working now. So back to kind of where we started. Although here we see this particular one was finally one that wasn't green here. It's actual is acceptable large, and actually this looks pure large. Okay, so let's run the sort here. And oh, we got quite a few rejections or bad errors here right off the bat, but we see mostly green. And so what we're doing is we're running each of these batches, and these are the images and the predictions. And so then what we're going to do is we're going to get a percent of bad errors. So of these 200 runs, what percent are red? So where it's actual is reject and the predicted is acceptable. And it says 13% error. So this is for a training set of 8,000. So now we're going to work up, and you're going to work through this run this 3 times, get an average percent error. Then let's load another model, and another one, and another one. I'm going to jump up to the 64,000. Notice the Keras file, the training file itself is the same size regardless of what the training size of the training set was, but it's still very large. And then we should get a pickle file coming up here. Okay, and we'll just do a batch inspect. Okay, so we're going to do a run sort. We got 13% error here. Let's see how this does with the 64,000. So mostly green. There was a red. There's a blue. There's a red. But you can see here, getting it right most of the time. And image 200, and we get a 5.5% error. So again, run each of these models and then plot the percent error as a function of the size of the training set, and see what it looks like. See if we get diminishing returns at some point. Like I say, this one we just ran it on took 14 hours of my computer pegged out at 100% CPU, almost 100% RAM usage. And so a very demanding training. The 8,000 took, I think, 26 minutes, something like that. So a big difference in the size of, or the time needed for the training. Just in the extreme difference, I'm going to load now the 2,000 images. And so there's the Keras file, and then we will get the pickle file. And let me go down here now, and we will see we'll get much worse results. A lot more red coming up here, almost no green. And all this is just a different model looking again at these. So here's the first green. So big difference going from 2,000 pictures to 8,000 pictures. And then much less of a difference going from 8,000 to 64,000. So see what the percent is here. 52%. So over half of the images were just dead wrong. And then most of the other ones were wrong, but just acceptably wrong. Okay, so I think that's it for this lab. So write a conclusion. Here's some reflection questions that you can look at to help you write your conclusion. Try to have a good sense. You don't need to have a good sense of just how the convolutional neural networks work. Just an overview that the convolutional neural network looks for features in images. And we can see here that the larger the training set, the better. Now we will, in the final lab here, go back to convolutional neural networks, and we will really hit this idea of overfitting, and we'll actually see the consequences of overfitting. So we haven't been able to see that yet in our labs, but the last lab in the sequence here, that will arise for us. All right, so until then, I will stop this video and see you in the next lab.